Welcome to this lecture series in linear algebra. In this lecture, we learn about normal operators, and let us recall some of the things that we will need. So first, we need the notion of orthogonal projections. So throughout, V will be some inner product space. I'm not writing that. So a linear endomorphism on V is said to be an orthogonal projection if one can find a subspace U of V such that P is the projection on U with respect to U perp. U perp is the orthogonal complement of U. So that's the definition of orthogonal projection. But a criterion to check whether a given endomorphism is an orthogonal projection is this. So given a linear endomorphism on V, it is an orthogonal projection if and only if P square is equal to P and P is equal to P star. Okay, then we need the notion of trace. So recall, again, if we have an inner product space V, then trace of any endomorphism T on it is defined in this fashion, where E1 up to En form an orthonormal basis of the inner product space. So no matter which orthonormal basis you pick, this quantity does not change. We showed that and then defined trace in this fashion. So now we also know, we proved that trace ST is equal to trace TS. So this is a very important identity. So this is true for any two endomorphisms S and T. Okay, and this allowed us, the device of trace allowed us to define an inner product on the space of endomorphisms of the inner product space as follows. So you pick two endomorphisms, you declare the inner product to be trace of S star T. So this S comes first with a star and then T, and you take the trace. So this gives an inner product on this space. So if you have an inner product space, you get an inner product on a bigger space. Okay, so we will use these facts. Here are some problems for practice. This one is marked as star, not because this is hard, but because I'm going to use it. And the second one is also marked as star. So both these problems I'm going to use. And now let us continue. So what is the definition of a normal operator? I should motivate the definition of a normal operator, but I myself don't know any good motivation for it. It is, there is motivation in a post hoc manner. So once you read it, once you see it appearing at other places, then you realize that this is important. But as of now, without any preamble, this definition will seem like popping out of the blue. But I encourage you to just play along. You will need this notion as you continue to learn more and more math. So let's just get on with it. So fix an inner product space V and an endomorphism T on it. Then we say T is normal. We say T is normal if this equation holds, which is to say that T commutes with its own adjoint. That's what it says in words. So as I said, this looks like coming out of nowhere, and there is nothing much I can say. Okay, alright, so here is a simple note or exercise. If T is normal, then this is also normal for all scalars. So this inner product space could have been either real or complex, doesn't matter. If this is normal, then this stays normal. Okay, and now let us look at a concrete example of a normal operator. So fix a basis, the standard basis of C2, E1 and E2 is the standard basis, and define T via this equation. So T is the unique linear endomorphism of C2 which satisfies this equation, meaning its matrix looks like this. And then I want to say that T is normal. So how do you check for normality? You need to check that this equation holds, which is the same as checking that this equation holds. Right, this is what we want to check. But this is equivalent to checking that the product, this thing, right? So we need to check that this is equal to that. But now this is already given to us. What about this? Well, this is an orthonormal basis. So once we know the matrix of T with respect to an orthonormal basis, the matrix of T star with respect to the same orthonormal basis is just the conjugate transpose of this matrix, meaning you take the transpose of this matrix and put conjugates on every entry. These are all real numbers, so the conjugation will not do anything, but the transpose will happen. So now you just have to check that the corresponding two matrices multiply and give equal answers. So this is an example, and you can construct infinitely many examples. Okay, so they do appear. It's not some empty notion. They do occur. Of course, you could say identity map is normal, but that's boring. Okay. Now here is a nice fact. This has nothing to do with normality. This is just a general fact about inner product spaces, complex inner product spaces. So fix a complex inner product space V and an endomorphism on it. Then these two things are equivalent. So if T is 0, then clearly this holds. But if this holds, then T is 0. Okay. So let me give a proof. I'll give actually two proofs. But the first one is the kind of proof we haven't seen yet. It's kind of a trick. So just note that this thing, so fix two vectors, u and w. And then this expression is what? This expression is so this is just some check that this can be written in this fashion. This is called the polarization identity. That's all. So given this, and you can just do a mindless computation to verify this. Given this, you can see that B implies A, because if B holds, then this is 0, that is 0, this is 0, that is 0. And therefore, this would also be 0. But if this is 0 for each U and W, then T definitely is 0, because you could just substitute W as T of U, and hence T of U would be 0 for each U, and hence T is 0. So this is a tricky kind of proof, and it is good to remember this trick. Okay. Yeah, and A implies B, as we said, is trivial, so that's that. This finishes the proof of this fact. But here is an alternate proof, which is a less trick-based proof. So use the fact that there is an orthonormal basis of the vector space of the inner product space V, with respect to which the matrix of T is upper triangular. Right? Because so we showed this when we were discussing the Gram-Schmidt orthonormalization. We have a complex inner product space, so any endomorphism is upper triangulable. But then if you apply Gram-Schmidt's theorem, then you can show that there is an orthonormal basis which upper triangulates the endomorphism T. So you can just use that fact and then it will also pop out. Okay. So here, this actually leads to a nice criterion to check normality of an endomorphism on a complex inner product space. So fix a complex inner product space and an endomorphism on it. Then these two statements are equivalent. First is that T is normal. The second is this equation. So T of V has the same norm as T star V. Okay, so let's do it. So why does A imply B? Assume T is normal. Okay, so then by definition, which gives, so here we just use the property of the adjoint. This is T, so when it goes there, it becomes T star and so on. So we have that, and this gives us norm squared, but I will do away with the square in one step. So that's it. This is for all vectors V in it. So that's one direction, A implies B. And now for the other direction, let me not take another page. I will do it in a different color. So why does that happen? So we have assumed so under that assumption, we have for all vectors V, let me not write for all vectors V, it's understood. So this gives us that we are just reversing the steps in the previous argument. So now you subtract. Right, we just subtracted the two terms and wrote a 0 in the RHS. Is equal to 0, but this is true for all vectors V. And therefore, by the previous lemma, which implies normality of T, right? This equation means T is normal. So very simple argument, but yeah, we used crucially that previous lemma. Okay, so this has an immediate corollary. V be a complex inner product space, T be a linear endomorphism on it, then the kernel of T and the kernel of the adjoint is the same provided T is normal. So this is an immediate corollary of the previous one. Okay. And this is our last bit for this lecture. So fix an inner product space and an endomorphism on it. I don't know if I'll need complex. Probably not. Yeah, let's see. I don't think I'll need anything about complex inner product spaces here. I think this is true for both real and complex inner product space. Okay, so now U be a T invariant subspace of the inner product space. Then we want to say that U perp is also T invariant. You take the restriction of T on U, which is the legitimate endomorphism on U because U is T invariant, and then you take the adjoint of it. Or you take the adjoint of the endomorphism T, and then you can show that U remains T invariant under it. And you restrict, it's the same thing. And that this is normal. T restricted to U is normal. So these three things hold, where of course here crucially are in the hypothesis we have normality of T. Okay. So I will not prove all the three parts. Let me prove part A. And it has a very nice proof. The proof I want to give is something that I like very much. So part A, let P be the orthogonal projection onto U. Okay, so therefore, in particular we have P is equal to P star and P square is equal to P. So that we recall this. And now U is t invariant is equivalent to saying, so since U is T invariant, we have it's a trivial claim, just check that. And now as we had this star marked problem, or rather wait, so this was an exercise, the star marked exercise. It is this implication is pretty obvious. The reverse implication may require some proof, but anyway, this is an easy fact. So this was in a star marked exercise. What we want to show is that U perp is T invariant, and for that also we had an exercise. So showing that U perp is T invariant is equivalent to showing that this is 0. Right? This was the second star marked exercise. Okay. So let's call this something. Let's call this S. This operator will be denoted by S. Okay. So now our goal is to show S is 0. Alright. So what we will do is we will use the inner product on end V. There is an inner product on V which we denote like this. And the corresponding inner product on end V, which is the trace of, we discussed that. That also is something that we will denote like this. And that is an abuse of notation, but that's okay. So, okay, fine. So we want to show that S is 0. We want to show that S is 0. And therefore, it suffices to show that this is 0. Right? Which is what? Which means, by definition, we want to show that trace of S star S is 0. This is what we want to do. Alright, so now let's switch to another page, a fresh page where we will do it properly. Alright. So trace of S star S is what? This is equal to that's what it is, but note that P is an orthogonal projection, so P star is equal to P. I may remove that star. And this is also an orthogonal projection. This is the orthogonal projection on U perp. So this is also its own adjoint. So we may remove those things, right? So yeah, maybe I flipped the order. Okay, so let's instead of S star S, let's just do SS star. Doesn't matter. So we will show this is 0, and if you show S star, if you end up showing this is 0, this will basically show that this guy is 0. The inner product of S star with S star is 0, which means S star is 0, but that also means that S is 0. Okay, so let's do this. Hardly matters. Okay. So this is equal to trace right? We did not do anything. But now, since again this is an orthogonal projection onto U perp, or the orthogonal projection onto U perp, this square we can remove because it is its own square. Alright. So we have that, and now club these two things. So this much, think of it as a single guy. Okay. So what we get is this is equal to that, which is equal to right, which is equal to
Lux, find a waiter.
Alexa, stop. Okay, so it is equal to that. And yeah, so why did that happen? Because trace of the difference of two things is the difference of their traces. You can easily check this. All right. And now club this much. So this you think of as a single guy. And here also you think of this as a single guy. So now use the fact that trace of A times B is trace of B times A. So if you do that, this becomes right. This is the part that we clubbed. Right. So this is equal to all right. But again, P is the orthogonal projection on U. So this square can be removed and this square can be removed. So we ended up with this much. Okay, PTT star. Yeah, what happened to this P? I'm sorry. Sorry. I made a mistake here. There is no P on this side. Sorry about that. Sorry. Yeah, I think this is correct now. Let me check. I may have made the same mistake twice. No, I think this is okay. Yeah, this is okay. So we have that. And now, yeah. So, yeah, okay. So this is equal to something. So here we will think of this as a single thing. But what is PTP? PTP is, as we noted here, PTP would turn out to be equal to TP. That's because U is T invariant. Okay, so this is TP. All right. And now what do I do? I'm kind of lost, but let's see. This is equal to trace PTT star minus trace of, I want to manipulate this further, TPT star, but, okay, so yeah, fine. So this is equal to that. Now, why is that? Because think of this as a single guy. You just move it on the left side. Right, this guy comes here. The trace of AB is trace of B. Again, we are using that. So we have this, and now we have this difference. So PTT star minus PT star T, which is 0 simply because T is normal. So this is 0 and hence this is 0 and hence this is 0. And that's what we wanted to do. We have shown that SS star is 0 and hence S is 0. because this gives an inner product and blah blah blah. We have said this many times. So that's it. That finishes the proof of part A, and B and C are exercises. So that's it. These are exercises, and yeah. So as usual, like, comment, share, subscribe, and I'll see you next time.